Hello, my name is Reza Azad, and I'm happy to present our work for addressing the missing modality challenge on MRI images. The core idea of our network is shown here. Our strategy builds upon 3D efficient transformer blocks and uses a co-training strategy to effectively train a missing modality network. To ensure feature consistency in a multi-scale fashion, MMCFormer utilizes a global context agreement modules in its case scale of the encoders. Furthermore, to transfer modality-specific representation, we propose to incorporate auxiliary tokens in the bottleneck states to model interaction between full and missing modality paths. On top of that, we include feature consistency loss to reduce the domain gap in network prediction and increase the prediction reliability for the missing modality paths. Our network architecture follows a co-training strategy and utilizes two parallel networks. Both networks contain the same architecture, but they receive different inputs, where the first network operates on a full modality data, while the second network works on the incomplete data, where the objective is to guide the missing modality paths by the full modality network. As we are working on the 3D data, our network builds upon efficient transformer design to reduce the computational burden of the 3D processing. For each path, we create the network based on the unit-like structure with the strip connection paths. We also include modality-specific tokens and their construction head in our design, which we will present in the upcoming slides. Knowledge distillation modules. We propose three different knowledge distillation modules to distill the informative features from the full modality path into a missing modality network. First, we propose multi-scale context agreement, which we call MSCA module. Considering the rich representation of the full modality path, we aim to impose a hierarchical knowledge distillation module to the missing modality path to adaptively recalibrate its feature representation and minimize the domain gap. To this end, we propose the MSCA module, which seeks to minimize the context distribution between the missing and full modality paths in its scale of the network. To achieve this, in our efficient self-attention mechanism, we compute the global context, or GC, using the query and value vectors. To effectively align the correlation matrix calculated in both paths, we strive to minimize the distance between them. Next, we propose the modality-specific module, which we call MSP. In the previous MSCA module, we aim to align the feature distribution between the two networks. However, such alignment might surpass the discriminative modality-specific feature that existed in the full modality path. Therefore, we designed the MSP module to preserve discriminative feature in the full modality and transfer this information to the missing modality path. For this purpose, we define 4 modality-specific tokens on the network bottleneck, where its tokens aim to preserve distinctive features of its input modality. We choose bottleneck since it contains highly condensed, low-dimensional information of label maps, hence we can exploit it useful and distinctive. Besides that, the bottleneck layer summarizes a rich feature representation of the encoder into a lower dimensional and more compact representation, making it more easy to match the modalities and maintain the consistency between the two networks. Thus, MSP loss is calculated using the output of the full and missing modality tokens from the bottleneck layer. We further include the reconstruction head to ensure learning MSP in our design. Last, we include the consistency loss among the prediction of the network. A comparative performance of the network for different combination of these modalities are shown here.